It won't right. So, good evening, everybody, and I'd like to welcome Tomasz Liskiewicz, who's going to talk to us this evening on tribology. So, please introduce yourself and please feel free to get started, Tomasz.
Brilliant. Thank you, Amish. Thank you for having me, and thank you all for tuning in on a Monday evening to listen and talk about tribology. I really appreciate that. Especially that I spent last 25 years looking at tribology and applying service engineering solutions to fight against friction and to deal with tribology. And I got into watches something like five years ago, so I'm still relatively new. I consider myself a novice in that space. But anyway, let me share my screen. I'll take you through some slides. Hopefully you can see my screen now. And what I want to do tonight is to take you through some very general introduction to tribology, and then, of course, contextualize this to watchmaking and link that to some of the watchmaking challenges. So, I think a good starting point is a definition of tribology. So the word tribology comes from Greek word tribos, which means rubbing or rub, and of course is with an added suffix of ology, meaning the study of. But the formal definition of tribology is the science of engineering, understanding friction, lubrication, and wear phenomena for interacting surfaces in relative motion. The word tribology maybe is not widely known, but tribology is present all around us every day. As soon as you have two surfaces and you have some relative motion between, there is a lot of interaction happening between those surfaces, and tribological processes take place. Friction leading to wear, and then maybe some lubricating processes that we would apply to deal with those challenges. So these are just a few examples of individual components where tribology plays a key role. So brake pads, gears, and bearings. These are slightly larger assemblies or products where tribology plays a role. Of course, watch movements, but also, bigger scale engines and gearboxes. And then moving on to manufacturing processes where understanding principles of tribology is a key to controlling those processes, especially in manufacturing, like turning, rolling, and grinding. So tribology is the most important subject no one has heard of. That was said by Professor John Tichy in Leeds more than a decade ago during a tribology summer school. But this is, of course, something that all we tribologists like to repeat often, as we know and understand that tribology is key to understanding the world around us. Always good to have some historical context, so let me give you some examples of early applications of friction. So what you are looking at is the illustration from ancient Egypt, showing a process of transporting a large stone statue. So what we can see here is a number of men involved in actually pulling the sledge with the statue, and a number of other team members, engineers, advisors, and so on around that. But there is a key figure in that illustration, just in the middle of that illustration, of that picture, standing at the top of the sledge, in the front of the sledge, is one guy who looks like he's pouring some liquid in front of in front of the sledge. And this is understood to be one of the first examples of applying lubrication to deal with friction forces and to minimize friction. I'll come to that example later on, but let me give you a few other examples. So ancient civilizations realized relatively quickly that they can generate heat by rubbing two dry pieces of wood. And then in 4th century BC, a major realization, the discovery that replacing sliding friction with rolling friction can actually decrease forces required to move objects significantly. And with that, of course, improving the uh, uh, civilization. More recently, Leonardo da Vinci is recognized as the father of modern science of tribology. And this is because he constructed, he conceptualized, produced a number of what we call today tribometers, so small devices which are used for measuring friction using different tribocouples, different weights, different geometrical arrangements. And in his notebooks, we can see some beautiful examples of those designs, and we know that he actually manufactured many of them and ran many of tribological experiments. So coming back to the word tribology, the principles of tribology are being known and recognized and looked at for many, many centuries. But the word tribology, definition of tribology, just happened very, very recently, actually in 1966 in the UK, in this country. So in that year, the government posed a question to a group of industrialists. And the question was, how much friction cost the UK economy? So the chair of that committee, Peter Jost, bring together a group of industrialists and academics that spent a couple of years looking at that problem. What they realized that very cost of friction, wear, and corrosion and surface damage due to corrosion to the UK economy is around, or was rather around 1.36 of GDP at that point. So really, really significant number, a number that government surely was interested in. But as a part of that working group and part of that report, the group realized that there is not really good definition of all the processes around friction, around surface damage, around wear. And as a part of that work, they defined word tribology. And as explained on our first slide, they derived that definition from Greek term tribos, meaning rubbing. So really, the modern tribology, in a sense, is a very, 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 very young discipline. Some 50 years ago, after the JOST report publication, two researchers revisited the JOST report and recalculated the losses due to friction wear to the economy. And actually, they arrived at a very similar number in terms of gross national product. It was 1.36 established in the JOST report, and in 2016, that was very close to that. It was 1.39. Of course, it was much more in terms of the actual cash 50 years later, but very, very similar ratio. The distribution in terms of where that energy goes in terms of friction and wear is very different. As you can see, after 50 years, we know much better how to deal with surface damage, with wear, with breakdown. We know how to increase lifetime of components, of machinery, but friction remains a significant challenge and still is consuming a lot of energy. I just want to show you one example of how tribologists improve your life if you are a driver. If you happen to have a car, internal combustion engine car, this graph is showing the fuel improvement and fuel economy of a standard passenger car. So in that case, it was a Toyota car. So On x-axis, you have time in the 80s, 90s, and early 2000s, and on y you have percentage of fuel economy improvements. So we can see that over years that improvements were increasing and increasing, and you can see a number of different discoveries, wherever it's new lubricant composition, wherever these are new materials and coatings like titanium nitride, or maybe new design solutions. Those discoveries contribute to better fuel economy, and this is the type of work that tribologists would normally do. So tribology, friction, where all those processes take place on the surfaces. And as long as we start looking at surfaces, we get into trouble because surfaces are very, very complicated. Even if they don't look like, they are very, very complex. And this is why Wolfgang Pauli said that God made the bulk of the material, but surfaces were invented by the devil. So a surface like that work example here might look very nice, very shiny, very innocent. But if you look at it with some magnification, you will realize that there is some complexity. So starting with surface roughness, you realize that even if surface looks like a mirror finish, there is some underlying roughness if you use powerful enough methods and instruments. And this is the place, surface, where all the physical and chemical, electrical processes are taking place in terms of interaction of that surface with the external environment. And then even what the definition of surface is. We can just say that this is the plane which terminates and which defines the end of the border of the solid. But surely there is some termination effects going into the solid. So apart from the top layer of the surface, we should be considering a certain depth of the materials, at least a few atomic molecular layers beneath the surface. And if you start doing that and you start applying different surface models, you will realize that there is a lot of chemistry, a lot of physics going on, and actually that surface that you looked at from the top, when you do a cross section through that surface and through the material, you realize that there's a number of layers. There's oxide layers, absorbed layers, work hardening layers, and it's getting really, really complicated. So if there is only one slide that you remember from today's presentation, I suggest this is the one. So this cartoon captures in a beautiful way all the complexity happening between interacting surfaces. So what you're looking at is two components put together, and there is some relative motion between them. So we are clearly in tribology regime here. So first of all, you notice that those surfaces are not flat at all. There is that roughness that I mentioned about. It's microscopic level, but there is roughness. And then because of that energy, because of that displacement that we apply between those surfaces, there's a lot of interaction happening between them. There's chemical interaction, so you have some oxidation and corrosion. There's mechanical interaction, so you have deformation of those peaks and asperities. Because of that, you have phase transformations within the materials. You are generating some third bodies as a result of the wear. You have friction, adhesion. You might choose to introduce a lubricant, and with that, change the environment. And of course, that will lead to some other processes, chemical processes, and so on and so on. So beautifully complicated picture of a very simple interaction of two surfaces. So Monday lecture needs to have at least one equation, but it will be a very simple one. It's a coefficient of friction that maybe you heard about in the past. Simply, this is the ratio of the frictional force, which is resisting the motion of the two surfaces in contact. So it's a force parallel to your sliding plane, to the normal force. So basically, the applied force, it might be weight. So that's the ratio of those two forces. So let's now come back to the Egyptians for a second, and let's do a very quick back on the envelope calculations for that case. So if you want to compare the frictional force with the normal force, we can replace our F, which is friction force, with the amount of work being done by all these men pulling the sledge. So I think someone calculated that it's 172 men, and the tractive effort that they produce is our frictional force. And then let's assume the weight of that stone Colossus is approximately 600 tons. So with that, we would calculate that coefficient of friction in that case is around 0.2, 0.23 exactly. So that suggests that there is some lubrication going on, because for any dry friction case, you can achieve around 0.2 coefficient of friction only for the cases where you use some polymers, so which tend to be low friction materials. So you can see in this table here, polyethylene on steel, polyethylene on polyethylene, maybe nylon will give you around 0.2 coefficient of friction. For any other steel on steel, chrome on chrome, maybe glass on steel, you are getting much higher dry friction. So there is definitely some lubrication going on in that illustration. Right. So when we discuss tribology, we have to mention surface engineering. This subject is related to surface science, surface metrology, but we today would like to consider surface engineering as surface finish and applying some coatings and materials on top of the component so that we change its appearance, but more importantly, we change its properties, and very often frictional properties. So this is the typical diagram that I would show my students during the surface engineering lecture, just summarizing all surface engineering methods that I want to teach them. Of course, you don't need to look at any of them, and you don't need to read through that. The purpose of that slide is just to show you that there is a very wide selection of different surface modification or surface coating methods. You might be familiar with one of them, actually, the one sitting in the middle, called PVD, physical vapor deposition, as this method is tend to be mentioned in various aspects when it comes to watch cases finish. You might heard about DLC coating, this black looking coating, or maybe other colorful coatings that are typically applied through PVD method. So when we come back for a second to that cartoon showing two surfaces in relative motion, surface engineering is helping to deal with some of those processes. Let's say we want to decrease friction by simply adding some extra material at that interface so that you achieve the properties that you are looking for. You might have coatings on both surfaces, and then of course that changes that interaction quite dramatically. And with those coatings, you can control that process. You can achieve the properties of the surface that you are looking for. Right, let's bring it to watchmaking. So perhaps many of you heard that apparently Breguet said to Louis XVI, give me the perfect oil and I will make you a perfect watch. The story goes that Breguet was asked by Louis the 16th to make a perfect watch, and that was his very answer. I cannot produce you a perfect watch without a perfect oil. It's not sure whether Breguet said that for sure, but it certainly sounds like something Breguet would have said. Actually, the fact is that the distribution of lubricants was mentioned in the patent for the tourbillon that Breguet submitted as one of the benefits of that invention. I came across that blog post in Revolution on that very subject, so I would suggest you can read through that if you are interested. But it seems that the perfect oil for Breguet would be, in fact, a solution where there is simply no oil or there is no need for oil, which I think would put him in a very interesting position nowadays, where we try to get to that point. So moving on to Čapek, I come across that publication by Franciszek Čapek, actually written in Polish. As we know, he was working very closely in early days with Antoni Patek, another Polish guy, and I think at that point is of the early collaboration. Čapek, who was originally from Czech Republic, he published in Polish. But anyway, he recognized the importance of resistance, known as friction. He related that, and he described the process and relationship between that resistance and smoothness of the surfaces, especially of the pivots that he looked at, and the relationship between that process and the accuracy of the watch. So fascinating read. For many years, there was a really great website by Rolex, specifically on tribology. A couple of years ago, it disappeared. I don't know why. But as a tribologist, I really liked that page is there, because Rolex was describing tribologists like artists, like people who really make watchmaking possible by extending the lifetime of the mechanism. And it was very more romantic description of tribologists, which I really enjoyed. But anyway, that website disappeared for some reason, but you can still read about Rolex and their approach to tribology. They are no shy saying how important it is for the performance of the mechanisms, using high quality lubricants and some novel materials, and making sure that their movements are reliable and durable. There is some evidence of academic research on tribology of watches, but I have to say very minimal. I only came across a few papers, research papers on tribology of watches, like this one from colleagues from France. So they looked specifically at the Swiss lever escapement. They ran some dynamic analysis, measured some speeds, interaction between the gears and the pallets, and looked at the degradation of the materials, and formulated the degradation models. So really interesting study, but as I say, not many examples of that type of research being published. And I think we all understand the commercial aspects and of that research not being publicly available. So let me finish off by just bringing three case studies where different tribological solutions play a significant role in the design of a mechanism or a watch. So let me start with this Panerai. 1950 Carbotech. So this watch is special from the tribology perspective because Panerai claims that all the main plates and bridges are constructed of tantalum-based ceramic, which apparently removes the need for any kind of lubrication in this watch. There is also DLC-coated silicone escapement. So DLC is used here not only as a finish material on the case, on the external of the watch, but actually inside the movement. Um, there is also elimination for the need for any additional jewels with that. And there are only 4 DLC coated jewels that remove need for lubrication again. That makes sense. DLC is low friction coating, which is used widely in the automotive sector, other sectors. So certainly is helping with controlling friction here. And the last but not least, their 2 mainspring barrels also operate without any grease due to that presence of DLC coating. So that's a first example, mainly focused on application of surface engineering solutions. So in this case, DLC coating inside the watch mechanism. And now taking us completely on the other side of the spectrum, so from no lubricant to a lot of lubricant and Resonance ROX module, which is entirely filled up in that upper half with the lubricants, and all parts are suspended in oil. And Resonance is claiming that with that they achieve constantly lubricated regime, resulting in very, very low friction between the parts. And the third case with Eterna Sphero drive, which is using ball bearings to ease the movement of the barrel. So very, very small miniature ball bearings, quite innovative solution, which not only minimizes friction wear, but also doesn't require lubricant to operate and improves efficiency. I think we'll stop here as Hami suggested that maybe that's about as much as we can take on Monday night in terms of lecturing people on tribology, but I will be more than happy to take any questions. And again, if you want to remember anything, please remember that cartoon. So wherever you brush your teeth, you drive your car, or maybe indeed you wind your mechanical watch, this is what's happening during that that very time. So thank you, and we'll be happy to have a chat about tribology if there are any questions.
Yeah, thank you very much. That was very interesting. Um, I guess my first question is which part of this science interests you the most? And does that relate to watchmaking?
So I was drawn into surface engineering as a way
Mhm.
of coping with friction and dealing with tribology challenges. So different surface engineering techniques. I spent a lot of time depositing coatings, characterizing them, measuring, running tests on tribometers, including DLCs.
And that's what you're currently doing.
Yes. However, as a head of department, I don't have that much time to spend in the lab, but still have few projects going on around that subject.
Okay. And so can you help me understand like why the difference is so large by adding a coating to a wheel rather than a lubricant?
So with any coating, with any surface engineering solution, you are using your component substrate as a carrier of your coating, and the properties of that substrate material can be so different from the coating that you can be using a very cheap steel material and just focusing on that top layer, which very often is, 1 micron thick, 2 microns
Right.
thick. And with that, completely changing the mechanical, physical, or chemical properties of that component. So that top layer, will completely change that functionality that you are looking for. And depending on the application that you're looking for, you need to design your coating. So if you are looking for low friction, that will might be one of the DLC coatings. If this is the appearance for consumer product, you want shiny gold or shiny silver surface, there will be another coating for that. If you need to protect against corrosion, again, another coating, another manufacturing method.
Hmm. And
Tomasz, thanks for a great talk. I really enjoyed it. The question I would like to ask you is about research on the molecular and atomic level. Now, you spoke about kind of not much research, or it's not been done publicly, and Rolex's innovative approach perhaps might have even looked into that. But do you know anything about sort of where looking at kind of more chemical, the chemistry involved in this, where it's kind of going?
And I guess you mean specifically in watchmaking rather than broader tribology.
Oh, well, the whole thing,
Yeah.
everything.
Okay. Yeah. Yes. Great question. Thank you. The chemistry mainly comes into play when you start using lubricants, because this is the medium where you would put a number of different additives. And with those additives, you want to achieve, again, certain functionality. So with that, you might have a corrosion protection, or maybe you will change the viscosity of your lubricant. Um, um, so this is mainly where the chemistry takes place. In dry friction is less so. However, you will have some oxidation. You might have some debris generation. Those debris can be oxidized as well. So there's that aspect of chemical interactions.
Mm. Is there anything looking at the what do you call it, the sort of reaction between the two surfaces other than what you've already outlined, but more on a sort of atomic or molecular level?
Yes, for sure. However, it's really difficult to measure that through experiments. More often, this is done through numerical simulations. So molecular dynamics, for example, you would model a situation where you have two asperities in the contact, and run a computational model which will simulate that interface with all the chemical reactions taking place at the interface. In the experiment, in the lab, it's more difficult to achieve. However, you have instruments like atomic force microscope, for example, where you can achieve those nanometer scale contacts, and run some experiments very often in vacuum.
Thanks.
and a lot of watch companies are using more silicon parts, and I'm never clear exactly why they're doing so, whether it's the main benefit is is wear and tear. Can you enlighten us a bit more about the ever-growing increase in silicon components, please?
Yes, you can see that in many marketing materials, and as soon as there's silicon mentioned, there is that aspect of novelty, and new materials used, and some added value. So uh, I guess the main case around silicon is that you can control friction to much greater extent. It's a lower friction, and it's kind of more sophisticated, and more expensive material than steel, and that's perhaps as simple as that.
And do they design different types of silicon, or do they then coat the silicon?
Um, well, you can coat pretty much, or you can produce pretty much any coating out of any material through PVD method.
Right.
But I'm sure it's bulk silicon rather than coating. If possible, you would like to avoid applying uh, coating, especially on elements like maybe cases where you can scratch the coating and coating can fall off. Um, as you know, it's been discussed in the community, especially in relation to DLC coatings, how easily they can get damaged.
Hmm. And you gave us three
Another
examples.
I have
question.
a
No, go ahead, Wolf.
Yeah, no. In relation to built-in obsolescence within industry as a whole, the broader sense. I would, like the watch industry is sort of the luxury watch industry is one where this kind of science is important. It would contribute to the appeal of the product, but I mean, perhaps also high-end car, engines and. But in terms of the broad appeal of tribology, uh, is it really been taken up by industry as a whole? Because obviously, if you make a product that lasts forever,
Hmm.
it's not in everyone's interest to have that.
Yes, I think there's also a question of price, how much
Yeah.
R&D would go into those mechanisms. And this is perhaps we hear about, Rolex and others investing heavily in that area. Yes, I think the bottom line is, to get to the point where the service of the mechanism is not required, for 50 years, whatever, because the durability of the components is such that, you can keep it going for a long time. You don't need to replace a lubricant. But I think you alluded to car industry, you have whole range of cars and price points, and depending on the technology used there, the price kind of correlates to that.
Okay. I think Waldo has a question first and then Mark.
Thank you, Hamish, and thank you for a fantastic presentation. My question, a bit more about watchmaking, I guess, is that I was speaking to somebody that and asked them about their PVD coating on the cases that they'd manufactured. And he went into explaining, I don't know so much about PVD coating, but he went in and explained how it is used as well in industry for more often rather than just coating for decoration, but for coating for lack of friction. And I wondered, and he couldn't answer at the time, was whether you could coat pivots or pinions in a PVD coating,
Mm.
which would obviate oiling, which you sort of semi-answered with the Panerai
Mm.
example,
Yeah,
making bridges out of it.
yeah,
But that sort of, but actually, could you coat steel pinions, hardened steel, pinion steel, with just the tips, as it were, with PVD to
right.
obviate oil?
Right. So the PVD coating is a line of sight process. So basically, you need to see the surface that you want to deposit on because of the nature of the coating, let's call being, sprayed, let's call it that way. So the only geometry that you will have a problem coating is deep recesses and holes, kind of long, small diameter holes, because you won't be able to kind of penetrate and look in there because it's line of sight process. So anything that can rotate, that you can expose the surface of to that process can be easily coated.
Okay, so you
Yeah.
could actually wear the pinions, the pin that's holding the wheel, and the
Mhm.
pinions where the wheel teeth engage, where historically there's enormous friction which detracts from the accuracy. You could coat those surfaces in PVD and make them much easier to turn, in effect, and much more frictionless.
Yeah, you should be able. I think the challenge with those small components is that the typical PVD process takes place in a relatively large chamber. You need to, manipulate and install
Yeah.
those very small components in the center of the of the chamber, and produce the conditions, the deposition conditions that will produce uniform coating. But as you alluded to, the example of Panerai, it's been tried, it's been done. It seems like it's not, mass produced. This at the end of the day, I think it must be expensive when applied to individual components. I think in that case they only produce 50 of those watches, and of course they are very expensive. But in principle, possible.
Okay.
Thank you.
Thank you very much. Thank you, Hamish.
Mark for next question, and then Jamie after Mark.
Hi, as everyone has said, thanks for an amazing talk. Unfortunately, I missed the first 15 minutes, so I do apologize. My question's really about the George Daniels or Omega's coaxial escapement. Obviously, that was designed to reduce sliding friction between the escape wheel and the pallet stones. I just wanted to, I suppose, get your take on the fact that they've gone down a particular route to reduce friction in terms of changing the way traditional Swiss lever escapements work. Obviously, Rolex went down the route in terms of, from what you said, in terms of improving or changing lubrication. Just from your experience, I just wondered, I suppose ideally you can go down both ways, but what your thoughts were of changing the way the lever escapements worked in general. And so reducing friction that way, if that makes sense.
Yeah, yeah, no, great question, Mark. So, well, as I mentioned, still novice in that space in ology, but so the coaxial escapement, I think we can classify or characterize as a design solution, changing dramatically the design of the lever escapement and the geometry, and with that controlling the kind of the amount of friction that is taking place, or the energy that is dissipated through friction. So changing the design, and with that kind of fundamentally changing uh, the interaction between the surfaces, and the energy that goes into that. Well, I think uh, the other situation is more about uh, changing the materials involved and the lubricants involved in the tribology process, rather than changing the design. So I guess this is perhaps as far as I can go with that question. So tribological improvements due to lubricants and surfaces versus design, completely new design in case of coaxial movement.
Thanks. I mean, I guess a combination of both might be the best way forward.
Mm.
And I think you alluded to that with the Panerai example. Although that wasn't necessarily design related, but I suppose one final question, given what you know, and I don't know how much of a watch collector you are, but given what you know, would you choose an Omega over a Rolex? I don't need an answer. It's just of an interest to me whether you'd go with the
Yeah,
design or the
yeah.
or the improved lubrication.
So look, let me answer that question that way. The first watch in my collection was coaxial movement, Speedmaster Professional.
Thank you. But mine too as well. So thanks.
Thank you. Thanks, Mark.
Jamie, go ahead.
Hello. Thank you for a lovely talk. It was really good. I just wanted to ask if sorry, can you guys hear me? I don't know if
Yeah.
I've got the mic on. Oh, okay, sorry. Is there any books you can recommend on tribology and for movements in general. So I was looking at Swatch as an example. So their System 51 movement has got
Mm.
51 parts in it. Is the push towards less parts, is that an asset to tribology, or is that the thing you're striving for as an engineer, is to less moving parts is the aim, I guess.
Yeah, good question, Amy. So, yes, at the end of the day, the less interaction you have between surfaces, the better. I think that particular system, yes, indeed, I think there are only 51 components. In that particular case, I think they're mainly polymer, made out of polymer, so not the best material in terms of durability, but definitely important development in terms of decreasing the number of components and complexity. Uh, in terms of books, yes, lots of them. Um, More on the tribology side of things rather than tribology in watchmaking, which I think it's a shame. So I think I need to look into that and maybe fix that.
One last question as well, sorry. Where do you see the future of watchmaking going in relation to tribology in terms of like processes, I guess? Like, I think it's quite a broad question, but like
Mhm.
through other areas of engineering, what sort of processes do you expect to move towards watchmaking?
Yes, with those processes becoming more ubiquitous and kind of cheaper, I think we will see more advanced materials in popular movements, which must be a good thing. So with that, reliability improved and lifetime of those components improved. So I guess perhaps that direction. So more advanced materials, more coatings being used in the in the production of standard mechanisms, and with that, all independent brands being able to use those mechanisms and use them more widely.
Oh, thank you.
Just to put it in perspective, the more brands are able to use silicon escapements because the first set of patents on those has already expired. And in terms of what do brands do? So when Rolex last updated the standard oyster perpetual movement, which I think was 2013, no, later than that, but I can't remember the exact year. But they stated that in that new movement, which is just the base automatic movement, 99% of the parts were new.
Mm.
So, what do they spend all their time doing? They spend their time doing that.
Yeah, yeah.
Work trying to make it more reliable, basically. They're not trying to make it prettier, right? Because that's all on the outside. So
Mm.
so in the industry there is a huge amount going on, but as Thomas says, unfortunately it's all kept secret, or almost all of it is kept secret. Um, so I wish Thomas luck in ferreting out some of the interesting aspects of what they're doing. Um, and I know that Roger Smith, he of a watchmaking fame and based in the Isle of Man here in the UK, his life's goal is to make a frictionless escapement. And he said that repeatedly in his public lectures on his evolution of his escapements and the evolution of the Daniels escapement. And then we've also seen, in the club, we've done events with the double impulse chronometer, where instead of friction, there is a hit. Like, that's the simplest way I can say it. So in that movement, the goal is not to have a slide, but to have a hit. And two different firms, Frodsham and Lederer, completely different double impulse chronometer escapements. And they're sort of fighting it out in a very, very expensive high horology battle as to whether the movement is reliable and better at timekeeping. So there is a lot going on, and I would greatly encourage anyone to look into it, including you, Thomas. It'd be great to see some work from you about it in detail on watchmaking.
Yeah, absolutely.
Does anyone have any other questions at this stage? No. Well, I think that's been a fantastic talk. So thank you very much for your time, Thomas. Thank you for putting the presentation together. It was very interesting, and now we can try and find some other people to ask tricky questions of in the watch industry.
Pleasure. Thank you for having me, and thanks for great questions.
Thank you. Hope to see you at an event soon.
For sure. Thanks.
Goodbye, everybody.
Goodbye.